Standard error of the estimate. Here are two regression examples. You can see that in graph on the left, the points are closer to the line than they are in the graph on the right. Therefore, the predictions in graph on the left are more accurate than the graph on the right. The standard error of the estimate is a measure of the accuracy of predictions. Recall that the regression line is the line that minimizes the sum of the squared errors of prediction, also called the sum of squares error. The standard error of the estimate is closely related to the sum of squares error. Specifically, the population standard error of the estimate is equal to the square root of the sum of squares error divided by n. Going back to these graphs, we can say the graph on the left has a smaller standard error of the estimate than the graph on the right. Now let's look at an example. Assume the data in this table are the data from a population of 5 xy pairs. Y prime is the predicted value and yy prime is the error of prediction. The last column shows the squared errors of prediction. The blue numbers in the last row are the sums of each column. The sum of the squared errors of prediction is 2.791 and n is equal to 5. Therefore, the standard error of the estimate is the square root of 2.791 divided by 5, which equals 0.747. On the left is a version of a formula for the population standard error of the estimate in terms of the Pearson's correlation. The Greek letter rho is the population value of Pearson's correlation, and SSY is defined on the right as the sum of squares differences between the values of y and the mean of y. For the data presented earlier, rho equals 0.6268 and SSY equals 4.597. Therefore, using this formula, the standard error of the estimate is equal to 0.747. This is the same value that we computed previously using the other formula. Similar formulas are used when the standard error of the estimate is computed from a sample rather than a population. The only difference is that the denominator is n-2 rather than n. The reason n-2 is used is that two parameters, the slope and the intercept, were estimated in order to estimate the sum of squares. If our data had come from a sample rather than being from a whole population, we would divide by 3 instead of 5, and the standard error of estimate would be 0.964.